Suppose you write some code, in this case a sorting function, and you want to know if it's correct. There are a few different things you might ask. Is the result ordered properly? Do we lose or gain any elements along the way? In other words, is the result a permutation of the input? Does the program crash when we try to run it? To answer these questions, you might write a test like the one written here. This is a reasonable place to start, but it doesn't completely answer our questions. In particular, we only know that our function is correct for this particular example. Unfortunately, if we continue with this example-based approach, there are a lot of examples that we might want to check. We can start with corner cases like the empty list or a list in reverse order. But at the end of the day, there are infinitely many lists that we could want to check. It's difficult to know in principle which examples we should care about and how many we should try. Even if we do settle on a set of examples, do we really want to write all of that code? The cleanest, most abstracted version of this approach is still pretty complicated if we need to choose all of the examples ourselves. This is one of the motivations behind property-based testing. We take properties like the ones we had before, for example, the list is ordered, and we write them down explicitly. We can read this code as, if we sort some arbitrary list x's, the resulting list y's is in ascending order. Rather than write an example of correct behavior, we've written the code to directly check one of the properties we care about, abstracted away from the particular test input. At this point, you might be thinking, okay, but this isn't a test. Where does x's come from? The answer lies in this given annotation. The annotation, which is provided by the hypothesis library, tells the testing framework what type of inputs this function expects, in this case, lists of integers. When we run the test, hypothesis generates hundreds of random inputs and checks our property with all of them. We don't have to think of the examples ourselves, and we also don't need to write code for each example we test. If we wanted, we could leave our tests running for days, and hypothesis would keep generating new random lists to test our code. With this framework in mind, we can go through and turn each of our correctness conditions from before into concrete properties. These tests make it really clear to observers what we mean when we say our code is correct. And we can spend as long as we like trying different inputs to make sure that the code actually is correct. This video is really just the shortest possible taste of property-based testing, but there are plenty of great resources if you want to know more. QuickCheck is actually the original property-based testing library, but I thought using Hypothesis for my examples might be more accessible. Both libraries have great documentation to help you get started. If you want a much deeper dive, John Hughes has both a paper and a talk titled How to Specify It, which I can't recommend enough. I'm also planning on doing more property-based testing videos on this channel at some point, although I'm a PhD student, not a YouTuber, so I can't make any promises. Thanks for watching.